Welcome, everyone. I think the previous talk was an excellent sort of discussion of the challenges in this space. And I think no coincidence, they were put together in this track here. It really leads into sort of these challenges that we sort of see in this observability space. And the big one is that data volumes are growing year over year. And teams are having to deal with this, like Joanne's sort of having to deal with this, come in and make sort of challenges and changes to the team, changes to the infrastructure to reduce this data rate growth. And a lot of this is, we're just building more complex applications today. We've gone from monoliths of yesterday to microservices to serverless functions to the edge. And the teams are dealing with this sort of just general concern of cost growth. And it's just a persistent concern that teams are dealing with on a regular basis. And there's a small number of vendors in the space, and they've coupled the storage with the analysis, which makes the sort of ingestion-based pricing difficult to sort of control those costs. And this coupling has also led to the fact that it's hard to drive insights beyond just the operations and uptime of the site. So one of the biggest struggles is cardinality. So if you look at what is the watermark of what we should be spending on observability, 25% is usually thrown out there in terms of 25% of your infrastructure spend. And that means that things like server names, regions, endpoints, those are easy to measure. Those are fairly low cardinality. But as you start looking at higher cardinality things like tenant IDs, customer IDs, maybe your pod names, and then even going further with edge and Lambda infrastructure, you really have to make hard decisions on what you're keeping or throwing away there. And while you can sample some of that stuff, you're just not getting a complete picture. And secondly, this data is really useful for teams outside of operations. So if you look at a typical log line here, an operations team might look at what is the latency that we're getting from this endpoint? What are the error counts, the response codes that we're seeing? But there's a lot more value here. And you should be able to unlock this value for those other teams. But sending this data into your typical observability vendor means that that data is really hard to query. And this means other teams are building parallel pipelines to extract this data, or they're just missing out, or using less useful sources like client-side instrumentation that's blocked by ad blockers. So it's challenging that all this data is sort of locked in observability vendors without unlocking the power to these other teams. So that's why we believe that there's some fundamental changes that are required in both technology and the architectures to meet the challenges of tomorrow's observability. So that brings us to our talk, which is we want to explore taking this telemetry data and storing that in cloud object storage. So we're going to walk through this. I'm Mike, and this is Ray. We are both co-founders of Streamfold. So if you are walking through some of these challenges, Streamfold is building a programmatic telemetry pipeline that allows you to send your data to multiple destinations, allows you to control, filter, rate limit, sample that data, as well as, and we get into, help you build out data lakes if that's what you're looking to sort of experiment with. So when we're talking about sending data into cloud object storage, we're talking about this concept of a telemetry data lake. We're going to cover sort of the pros and cons of that, and then through this talk, sort of walk through actually building one of these from first principles, and sort of show you what the file formats and indexing is required to actually build this and query this at speed. And we'll finish with some future challenges in the space that we think the industry needs to look at, and we'll advance sort of this space. So telemetry data lake is really taking all of your telemetry data, metrics, logs, traces, putting that all in one place that teams can query this and derive value from this from a single place. And the benefit is it separates your storage from your compute. So you can increase the amount of data you're collecting, and you're only paying the compute based on when you're analyzing that data. And you can scale that to 0 if you're not actually analyzing that data, but those aren't inherently tied in terms of the cost factor. It takes your ownership of that data back so that your telemetry data isn't owned from the vendors. You can store that where you need it. You can move it across vendors. You can bifurcate that across multiple vendors, cloud products, but you own that data. And then as you build layers on top of this, you can add the ability to query this data as you need. You can pull in other data sources and join that as you build on sort of layers on top of this vertically. And then simultaneously, you can meet some of the requirements that compliance needs for longer retention if you're storing that in sort of cheaper object storage. Obviously, we're sort of hand-waving through this. Getting data into object storage is just step one. There's a lot of careful planning to layer on querying, visibility, UI, alerting on top of this. So that's a much more longer conversation, but do keep in mind that, building out a vertical solution here does require additional planning and design. Part of the challenge, there's not a lot of standardized query interfaces for telemetry data in object storage. So you're somewhat going on your own path here, which means that you do have to consider what your visibility looks like, what your alerting story will look like. Lastly, of course, with anything, if you have requirements of GDPR, you will need to build some additional interfaces to meet those requirements. So let's walk through building this, and we're going to go sort of stepwise through what is the most simplest way to build this from step one. And we're going to work with a data set. This comes from an e-commerce site. It's a pretty active sort of set of requests across a number of clients. Because it is e-commerce, it's mostly GET requests. And we're going to do a simplified query here, which is we're going to select a time range. We're going to filter that to requests of certain type, GET or POST, and then we're going to group that by our method and response time, and then just count the total requests. So obviously the most naive way of doing this is JSON. So we're going to take our log line, and you can see the JSON schema here that we've converted to. Pretty simple, straightforward. We've come out with about 10 million log entries that we're using for this. We've converted it to NDJSON, and uncompressed, it's about 4.5 gigabytes. That's not big by any means, but for this demo, it gives us a good picture of sort of what we're dealing with here. And I've highlighted over here, these are the fields that we're actually going to look at to serve that query that synthetic query that we're doing. So to test this, we made a very simple Go CLI tool, just using the standard lib encoding JSON. We're reading from a compressed JSON file, and then we're going to scan the entries, matching those time ranges and the method for our filtering, record a result in a Go map, and then we're going to use an instrumented I/O reader to track the number of bytes read, so that we know how much of the file we're actually reading. So result is not great. It takes about a minute to go through both compressed and uncompressed versions of this. But the really highlighted part is that to read and analyze just those three fields, we have to analyze and we have to scan the entire file. So we're reading 4.5 gigabytes just to analyze about 150 meg of actual field values. So that's not great. So obviously, JSON is a row-oriented data format. It's not great for this sort of problem. So we really need a much more efficient file format. I'm going to hand that over to Ray.
Cool.
So walk through that.
Can you all hear me? Is this mic working? I can't tell. Is this on? You all hear me? Okay, cool. Yeah, so I guess we're sort of, so far we've done this locally. We're not talking about S3, but as you can imagine, when you're dealing with files, S3 is a great place to store a lot of files. Can I just get a show of hands here? Who works with Parquet on a regular basis or is familiar with it? Okay, so a few of y'all have been work with Parquet or have some experience with it. Just a little bit about the history. It's basically a columnar-based format. It's based on a paper called PAX. It was released in 2013, as we said, and it's open source and widely supported by a lot of platforms. The real sort of benefit of a format like Parquet is it enables efficient use of CPU cache and really optimized compression and encoding. So just a little bit on PAX, if anyone's not really familiar with it. The insight here was essentially when you look at traditional databases and n-ary storage mechanisms, basically all data was sort of grouped together in a row sort of format. So if I look at a page, I have a row header, I have, and then all my columns laid out sequentially. The problem with this is when you read a value from a row like that, let's say I'm trying to pull the age of each one of these individuals, you don't just read that byte from RAM into the CPU. Basically, it goes through the cache, and your cache ends up getting polluted with a lot of values that you don't need. So the key insight with PAX was, well, if I rearrange the way data is stored in disk and in memory, when I go to read a value like age in a columnar format, I get this benefit of the cache being populated with all of its other values of that same column. And so you have locality of reference, you have much faster use of CPU cache, and basically it's much more sympathetic to the machine. So Parquet basically builds upon that concept, and PAX, which sort of is underlying mechanism for a lot of columnar databases today, so like ClickHouse and Snowflake and the like. And basically what it does is it takes like takes your table format, it splits it into separate groups of rows, so separate groups of rows, and then from there it says, okay, for each of these row groups, let's create columns for each of these. It creates these column chunks. And then for each chunk of a column, basically, you have the smallest unit is a page, and this is where all this sort of interesting compression and encoding comes in. So now that we've organized values by column type, we can apply basically several different encoding techniques. In addition, there's also a lot of metadata inside the file itself. So there's Bloom filters, and there are zone maps that basically allow us to skip values. So we have the ability to say, look at this file and say, well, is the data I'm looking for in there? I have a predicate, and I can basically push that down and say, is it in this file? Oh, it's not. I can skip this entire file completely. Or it is in this file, but let's see, is it in these column chunks? No, it's not in this one because I'm iterating just quickly through these zone maps. That give me the highest and lowest value, and I know I can skip this. So this is where a lot of the optimization comes in. Mike, did you want to talk a little bit about the encoding a bit? I think you spent a bit more time on that.
Yeah, so the nice thing about Parquet is that it allows you to sort of decide column by column how you want to encode the data, which is nice because not all data types are the same. So we've highlighted about 3 of the sort of most popular ones here. I mean, so we have dictionary encoding. So if you have a field that's like a product name, you probably have a small set of those unique values. So if you build a dictionary, you can represent those by their sort of single integer values in that dictionary lookup, and then you store the dictionary. So that compresses it down rather than repeating a lot of those values. For integer values that are repetitive, run length encoding is pretty popular. So if you have a run of, say, the value 1 multiple times, you replace that with the repetition count, 3 in this case, and then the value. And you just repeat that over and over for runs of the same value. And then lastly, delta encoding, so timestamps in particular, where you have a set offset between values, is quite useful. So you store the base timestamp here, and then you just store the delta values off of that. You can also combine some of these, so you can do delta encoding and then do run length encoding on the delta, but these are sort of the basics there.
Cool, thank you. Yeah, so once we have our data, as we said, organized into the columns of the like types, it's really easy to say, oh, I've got duplication. And particularly with telemetry, you see a lot of values that are just constantly repeated, like zeros are repeated quite often, or values can stay the same. So you get a tremendous amount of compression benefit. So we look at Parquet, we took the same data set, and we wrote a little tool to basically convert this Parquet. And all of that will be, it's on GitHub, so it'll be available with the talk slides. But we went from, 4.4 gigs to 390 megs, so it's 91% reduction. Pretty impressive, right? And then actually essentially running the same query against Parquet as we did in the Go code results in a query time of 0.03 seconds. So it's much, what did we say the time was when we were going through the JSON?
Oh, it was like a minute, so
it was like a minute.
Significantly faster.
So we're just gonna do a little live demo for fun because that's much more fun than just looking at slides. So let's see if I can make this large enough. Can you all see that? Okay. All right, so we're just gonna load up DuckDB. Great embedded columnar database. So I can just do create a table. I have this logs.parquet file. We could recreate the file, but it takes a bit to create the file. It's like, 15 seconds or something. So it is quite CPU intensive when you actually go from like JSON to Parquet, but let's just load this up. So we're pulling that into DuckDB. It's pretty nice. Like we said, it's a columnar database and columnar format. So it's able to pull the file in and basically all these column groups. And then when you query it, it actually vectorizes that. So we can spin up lots of different threads and go, oh, I'm going to look at all these chunks, right? All these different column chunks and process those independently. And then it kind of waits to the end to actually perform the projection. So it's very, very fast. It goes through data really quick compared to row-oriented processing. So if we look at, let's see, select, let's see, okay. So if we run, this was the query we said we wanted to run. Yeah, it's super fast. It was like done almost immediately after I hit enter. But if we do an explain here, we can sort of see a bit more about what's going on. So we can see that the first thing that happens is that we're filtering based off of the timestamps. That actually gets pushed down to the storage engine, and it's looking at those chunks, and it's saying, hey, I only want these values. So it looks like we come back with 5 million initially. So we've already basically filtered the data set in half compared to, I think it was 10 million rows originally. And then we filter to get and post. And then here we have a projection where we say, okay, we want the status codes. And then we basically, those are hashed and aggregated. Then we get the final result. And it was actually 0.02 seconds this time. So very, very quick compared to dealing with JSON. All right, so continuing on, Parquet fast. But that's like one file. So I guess the problem then becomes you say, well, this is great, right? This stuff is really fast. It's really efficient. I could take all my telemetry, my logs, metrics, or traces, and store those in object storage. But like, how do I actually deal with many, many files, many Parquet files, right? So I knew what was in this Parquet file. I was able to load it up. I can put it on S3. But how do I deal with a lot of them? And so what we need is we need a higher level abstraction, again, like a table. So we've kind of like decomposed the database, but now we kind of need it back. We need to be able to think about things from a table perspective. And a lot of interest is going on in this area because people are realizing data lakes are great, but it's not really enough. I'm just throwing a lot of data in Parquet or ORC or different formats in the cloud, but I don't really have a mechanism to manage that. And so what we're seeing from a lot of vendors is there's a lot of insights coming from basically cloud data warehouse companies. And there's a sort of movement to unbundle some of this technology that's in things like Databricks and Snowflake. One of those things is table formats. So we'll talk about that real briefly. So table format is like Parquet. Instead of helping you work efficiently with a single file, it helps you work with many files. And it allows you to skip through files. Okay, I don't need to read those. Prune through files, modify values. Table formats have been around for a really long time, like a really long time. And they basically provide a logical abstraction or indirection over files on disk. You've used them, right? Everybody uses them when you create a schema in a database, but they happen to generally be bundled into an RDBMS. So once you have the table format and you can use it, pull that out, for example, and have that API, it provides us this nice API and that allows us to do things like schema evolution, hidden partitioning, and serializable isolation. So there's a famous table format that's pretty much the most widely used is the Hive table format. And basically the way it works is it's just pretty much simply a directory tree structure. What's great about it is it's easy to use. It's become a standard, and it can work with any type of file format. So you can put whatever you want in there, but it's got some downsides. So you end up with far too many directory listings. So if you imagine you're doing this in S3, and a lot of people roll their own table formats. They might define how they want to partition the data, use something like Dynamo or another database to basically create indexes, and then they say, oh, I can go look there, and then I can go look in S3 to sort of reduce the amount of queries I do. But basically one of the problems you have is too much directory listing. So you're doing a lot of metadata operations, like trying to actually find the data that you want for your query. And so the Hive folks recognize that, and they're like, well, we can add something to this, so we can create a meta store with a little bit more information about the files that are on there. But that you run into some problems because now you have two sources of truth, and you don't have, you can't do any atomic updates. So you could change the meta store, but have failed to write the file, or failed to write the file and update the meta store. So it's been a popular format, but a lot of folks realize, well, maybe we could improve on this and take this next step. So there's several formats out there. There's Delta Lake, what's the other, Hootie. But we're just going to talk about Iceberg today. It's a pretty popular one, and it's gaining a lot of attention. It's developed at Netflix. And really to sort of address, like we said, the limitations of Hive. It supports basically a hidden schema and partitioning. So it handles that partitioning for you of those files, those Parquet files on S3, and you get a lot of other nice things with it. Schema evolution. So if I change a column name, there's this layer of abstraction where it's like, oh, okay, I don't need to rewrite all the data. I understand that. I'm just changing the name of this thing. And so I can evolve my schema over time and basically put Parquet files or other optimized formats on S3 and use Iceberg to understand how that data is laid out to efficiently query it, skip files I don't need, and the like. So the key insight of Iceberg was to track, basically, as opposed to partitions, track all the files that are on there in your S3 or your storage mechanism. And anytime you want to write or make a change, the writer basically commits the new file and produces a new snapshot. So, and the way it does this is with optimistic concurrency control. So a reader will basically say, okay, I want to read the value from this table, and it follows this path down through till it gets to the data file and says, cool, I got a read version for this. Now I want to try to create a new version and commit that to the catalog. And if another writer has come along and actually modified the data, it will fail and we'll have to retry. So just stepping through Iceberg briefly, you have basically the catalog, and that it basically points to the latest metadata file that says, okay, what is the list of all the snapshots of the data that I have? And then you have each metadata file, it has information about all the files for that snapshot for that given point of time. And that points to this thing called a manifest list. And then the manifest list basically has a set of different files, so manifest files that ultimately report that point to data files. So really quickly, we can show you a quick demo of using Iceberg, and it's going to integrate with Parquet, and we can add data to it, and it sort of handles a lot of that logic for you, so you don't have to partition the data and figure out how to store it. So let's see. Okay. All right, so we're running Iceberg here. We're doing it locally. I'm using some Python libraries. It's pretty early in the Iceberg ecosystem. Basically, it's an open spec, and a lot of the implementations that are there today are based around Spark and other sort of big data tools. But a lot of people are building. The idea is to have this open spec that defines how Iceberg works, and then a lot of people are building for all different languages. So there's Rust implementations going on in Go and the like. So basically, let's just take a look here at what one of these Iceberg schemas look like. So we just have a little script here where we say, I'm gonna have my local catalog, and I'm using SQLite here. So I say, okay, and we're gonna store this stuff in SQLite. So that's our basically repository for our schema. And then I'm creating a new schema here for basically metrics. We're gonna call this table metrics. It's gonna have an ID, a name, and a value. So very simple. Let's take a look at that. So if we run that, There we go. Okay, cool. So we've actually created the table, and if we go look in the catalog, let's go in here. You'll see we have the catalog DB, that's basically an SQLite file, and then we have a thing called metrics.db. And, oops, let's go look at data points. Okay, and we get a directory called metadata, and we get this JSON file. So, okay, is that big enough? Right. Oh, is that hard? There we go. That's better. Okay, so basically we've defined the schema here in this file, right? And we have ID, we have name, we have value, and we have basically a partition specification. So we could say here, for example, we want to partition these values based off of ID, or we could say if there's like a month or week or year, we can provide the columns to specify how we want the data partition. And you see there's currently no snapshots because we haven't added any data, right? So let's quickly run. We got, what, 10 minutes left? Okay, I think we're doing good on time, yeah? Okay. So let's actually insert some data into this, and this is sort of like, you know, a bit more interesting. So if we run this insert, let's see. The insert basically, okay, so we're gonna insert 5 records into this, metric 1 and 2, and basically we're giving them different values. If we go look at our database now, we got a new directory called data, and it actually built, there's a Parquet file in there. So we inserted an Iceberg, it handled partitioning it and actually converting it to Parquet for the underlying file format for that data, right? And then if we go look at the metadata, now we've got a bunch more stuff. So we've got these new Avro files here, and we have new JSON files. So let's just take a look at the latest metadata file. Cool, okay. So now, right, we've got some new information in here. So we actually have a snapshot. We're saying, oh, okay, so we've altered the table, right? And we've said, okay, we've committed, and we said we created a new snapshot. We've updated that spec and say, hey, these are all the files, right, that are gonna be part of this snapshot of the data. And as you can see, it points to this manifest list, which is this .avro file, right? And we actually have some information about what happened. So we added data files. It says, oh, we added a new file. That's basically the Parquet file that got added. In that, we added 5 records, right? And so it keeps metadata about what's going on in the underlying Parquet files as we are mutating this logical abstraction we're calling a table in this case. So that's pretty powerful. And if we were to open up the Avro file, basically you'll see it points to the Parquet file. So it gives us this mechanism and a logical abstraction to treat all of this data, this telemetry data that we're thinking about storing on S3 in a much more, you know, tabular format that we're familiar with, as opposed to just compressing all this stuff into millions of Parquet files and slapping it on S3 and coming up with a weird sort of, how do I organize these into different directories? So it's much nicer. It gives us that sort of database semantics that we're used to. Do you want to finish with the future challenges?
Sure, yeah.
Okay.
So yeah, you know, that was clearly you know, a lot of info, you know, sort of covering from what sort of the most basic design of this could be, of throwing data up into S3 to really adding on that sort of indexing table formats to be able to query at a much larger scale. This obviously is like step 1 towards building, you know, a full vertical data lake and solution for yourself. But hopefully this is sort of provided a bit of an overview, intrigued interest in this sort of area. And yeah, it's sort of step 1 towards, you know, potentially building and looking at solutions like this yourself. Want to finish up the talk with sort of some future challenges in the space. So first is that, yeah, what we're seeing is that, you know, storage I/O over the years has gotten incredibly fast and grown much faster than sort of the CPU speed. So what traditionally you would use in terms of like block-based compression, so your gzip, your zstandard, over these files like Parquet, et cetera, that can actually become more restrictive to decoding and pulling these files back and loading them into memory. So we need to look at alternatives, whether that's improving on the encodings themselves, like the run length encoding, delta encoding, or using some mix of those or some heuristics over the data to sort of optimally actually select better encodings dynamically based on the data set. But the traditional sort of block-based compression can be restrictive at scale when pulling this data back from much faster I/O systems today.
Why was the reason for that? Obviously, right? So these formats were built around 2010, right? And they were built at a time when computers behaved differently. So what's the changes now? There's changes basically with storage and memory. That's like if I actually compress this data, it actually slows down the process in some cases, right?
Yeah, you're also just sort of chewing up the cache lines that are more efficient if you're pulling in data that's should be within the cache line. So compression can, basically dump your cache lines, remove some performance, and then the storage is just a lot faster. Is not as much a bottleneck. So you're not having to reduce that sort of storage footprint as much as possible. Also, we talked about variable run length encoding. It's very useful for reducing the size of these files. However, it's much more difficult to use the GPU to process and compute sort of SIMD operations over this data. Because run length encoding, you have to sort of sequentially decode that. So you sort of limit what you can use the GPU for. And again, as sort of modern hardware increases, GPUs are much faster, much more capable than yesterday. These formats should evolve to leverage that as much as possible, especially with sort of the move to AI, ML workloads and the very sort of sophisticated GPUs that are there. Also, sort of poor file layout means that you can't parallelize these operations as much. So again, you can't sort of split and parse and load these files as efficiently on a much more efficient GPU. And then lastly, we talked about Iceberg. Iceberg was really developed, when did you say, 2017, 2018?
Yeah, 2017, 2018.
And I mean, the workloads are really around sort of the data BI teams where concerns about atomic updates and consistency of the data are much more important. But if you're using that for telemetry data, that's much less a concern. Your schemas aren't changing that much. Metric schemas don't change that frequently. Similarly, logs and traces. So all of this sort of schema evolution, time travel, as well as sort of atomic updates are much less important in that sort of case. So if we pulled that back, can we design a simpler sort of metadata partitioning, tabling format for that? But it's also tuned then for the cloud object storage. So again, if everything's being pushed to S3, you do have to look at what are the costs for S3 API calls. So what are the cost model of cloud object storage? And can you optimize for that as well as optimizing for performance at the same time?
Yeah, we need to do a bit more research on that, but we think just from early investigations, possible like Iceberg maybe overkill for telemetry, for example, because I mean, the primary use case would be if I have a late arriving sample. So I've written something and like, oh, I only actually had a partial measurement. Then I had another measurement come in. I need to update that data. That is not necessarily the most common case. And if you're dealing with essentially serializable isolation levels every time you're making a change, and every time you write and commit new data, you're creating a new snapshot. Obviously, the bottleneck would likely be on the writer path, and they recommend like basically optimistic concurrency control for that database. In this example, I'm using SQLite, but you would imagine if you were doing this at scale, you might use something like a very fast key value store like Foundation DB, right? That provides that level of isolation, or maybe Dynamo even as well. So I think though that could get costly as well too with the number of operations, and you might not need that level of capability.
We're talking about append-only workflows for a lot
Right.
of telemetry data.
And sometimes it's never read. It's written once
Right.
and never read in some cases. So, yeah.
Finally, we're going to recommend these two papers. These dive really well into sort of the how these data formats have evolved. BetterBlocks actually has a implementation of much more efficient columnar compression. Check these out, great papers, and really highlight sort of the future challenges here. So thank you all. Been fun. Check us out. Again, if you have challenges sort of with observability, data and telemetry, you could roll.
Thank you.